two pieces, but we need some pieces that continuous empty. So OS should handle it some way.
If I load my process to the memory, okay, that's the first place where we need relocation. I mean, when you load your process to the memory, that's an act of relocation, right? You are giving an initial space, but it's a relocation space. Later, as is that we might have to relocate our process because the operating system might need my space for something else. Okay, the operating system might need to move my location to some other place in the memory, and that's relocation happens again. And sometimes, if I am blocked, if I am not running, the operating system might save my space to the disk and let the other processes run. When I am ready to run, it might reload my code to the memory, and that's another relocation issue. The user, the process itself does not know if it is being relocated or if it is sitting on the disk or if it is running somewhere in the memory. So this is all transparent to the user, to the process. All the process knows is that it is running some kind of a program. It doesn't know it is being relocated and that kind of stuff. Just like the processes doesn't know if they are being blocked, okay, or they don't know if they are being rescheduled. They think that they are running the CPU by themselves. It is the same thing. Protection and relocation. Protection and relocation is easier using the address spaces. So each process has its own address space, okay, independent of those belonging to other processes. Each one has their own address space. The address space starts from some value 0, and it continues to the maximum addressable value for each process, and each process sees the memory this way. Okay, so this idea of address space is very similar to the concept of processes. Just as the process concept creates a kind of abstract CPU to run the programs, the address space creates a kind of abstract memory for programs to live in. Okay, so the process concept makes the processes think that CPU belongs to them, the whole CPU belongs to them, and the address space makes this illusion to the processes for the memory. So these are very important concepts actually. Process mechanism is some kind of abstraction of the CPU. Address space is another kind of abstraction mechanism for the memory. And they are very similar ideas. With the process concept, we have multi-programming. Okay, we have when the process blocks, other process can start, and the same CPU can be used by many processes at the same time. This is the advantage of using the process concept. When we use the address space concept, the same memory can be used by different processes without knowing that other processes are using the same memory. Okay. Same kind of abstraction, different mechanisms. Okay, any questions so far? Okay, good. So let's continue these address spaces. To implement the address spaces, we have the simplest mechanism, base and limit registers. This is one mechanism that we use to create the address space. Your homework is using this one. Your new homework number 2. You are going to use base and limit registers. Otherwise, in the first homework, you had a single process, right? Just one process. It runs and it halts. That's it. But in the new homework, you will have more than one process, 4, 5, 6, 10, whatever process at the memory, and each one thinks that they have their own memory. Okay, because when they say that jump 100, you should not jump to some other process's memory location. It should be in the same address space. So you're going to use the simplest way of abstracting the memory, base and limit registers. It is called, actually it's a version of dynamic relocation. Remember, this was the static relocation. In the static relocation, while you are loading your program, you modify those addresses on the fly. That's called static relocation. And the dynamic relocation, when you try to, in the dynamic relocation or the base and limit registers, we have two special registers. One is a base register, one is the limit register. So each process has its own base and limit register. When a process wants to access the memory, okay, the address that it tries to use is added with the base register, and it is checked against the limit register, okay. So maybe a good example here. Okay, this one. When this one says jump 28, okay, when this says jump 28, this number is added with this base register value. So it jumps to this position because 28 plus this value is this value. So it works. It actually, after doing that, when it says jump 28, these two numbers are added and this one is obtained. When it says that jump 40,000, let's say jump 40,000. When I say that, okay, this value is compared with the limit register. Since it is much larger than the limit register, the operating system will not let you jump to that location and a segmentation fault or the out of memory access trap will occur and operating system will end your process. So we have two registers, special registers for each process. One is the base register. These numbers are always added to these base registers, and one is the limit register. It is used for checking the address. Okay, so this maybe we can say this base register is for relocation. Okay, in the gözüme sarışık geliyor buradan. Gözüm sarı mı oluyor burada? Ortası beyaz sarı. Gözüme bir şey olacak şimdi. Video çekiyor mu ya? Neyse dinleyen yok zaten. Bu arada benim dinleme rekorlarımı kim kırıyor biliyor musunuz?
Üsfal.
Hayır, 222'ciler. 312'den dinleyen hiç kimse yok videoları. 252'ciler. Yanlışlıkla bu dersi dinledikleri de oluyor herhalde. Ne öğreniyorlar bilmiyorum ama geçen de senin derslerini şey yapıyorlar. So this one is maybe used for the relocation. The other one is used for the, remember two things, relocation and the other one was, we are after two things, protection. The other one is used for protection. Why? Because if I say something like that, this one is compared with this one. Okay. So one is protection, one is the relocation. Yes.
Hocam, base register'da limit register neden aynı? Hani limit register.
They are not the same. No, they are not the same. But they are same because this means that my process will start at position 16K, okay? And you cannot address more than 16K of memory. So for this one, for this process, base register would be 0, and the limit register would be what? You tell me. Base register would be same thing, 13. This value. Okay. So that means that you cannot address more than 16K of memory. It's the same thing. So it's a coincidence that this number and this number is the same.
Operating sistemden sonraki gelen kısımdan mı olması?
Anlamadım soruyu.
Base register operating sistemden sonraki kısımdan mı başlaması gerekiyor? Değişebilir mi?
It depends on your design. I mean, in this case, operating system behaves like a regular process, and it has its own base register and limit register. It could be anywhere, at the bottom, at the top, in the middle. So it's another. When you switch the kernel space, kernel mode, it runs another process, right? It has its own space. It has its own space. So the operating system should not access. Maybe I mean. It should not by accident access to some processes space, okay? So it has its own base register and kernel limit register. Okay? So it could be here or it could be in between. We don't know. That's the good part of the abstraction. When you do the abstraction, even the operating system would not want to know where it is running. Not the kernel stuff, maybe the helper utilities, operating system utilities. Okay, any other questions? So we are trying to abstract the memory. We abstracted the CPU with the chapter 2. We are trying to abstract memory in chapter 3. Okay, so Base and limit registers are good for dynamic relocation and map each process address space onto a different part of the physical memory. The process doesn't know what part of the physical memory they are using, right? The operating system gives you this help, okay? The contents of the base register is added to all memory references. That's what you are going to do in the homework number 2. And a memory reference larger than the limit register is invalid and it causes a trap. It causes a trap. It calls some kind of a special operating system routine. Usually, it will end your program if you are trying to access some other space. So these are the good features of the base and limit registers. The disadvantages, again, with the similar to the static relocation. Every memory reference is an addition and comparison. That's very costly. Addition is costly. It will take some time. Comparison is maybe easier, but addition is on the hardware is costly. So it's gonna slow your memory access times. It's gonna slow your memory access times. Also, another problem here is that if you have very large programs, they do not fit the memory. Let's say my memory is this much. My memory is this much, okay, but my process needs this much space. So with this base and limit register solution, I cannot fit this process into this memory. I cannot do it. But there are some other memory abstraction mechanisms that can make this work. I can fit this into this memory. What is the idea? The idea is you don't have to load the whole program, okay? Maybe you can divide them into pages. Maybe you can load 1, 2, 3, 4, 5, 6 pages. Load only 2 of them, okay? So when you are running this this program, run page number 1 and page number 2. And if you need the page number 3, maybe you can load it here because you don't need the number 1 again. So using base and limit register this way, I cannot run something sophisticated like this. So this is a much higher level of abstraction of the memory. The process thinks that it has a memory much larger than my main memory. In fact, my main memory is smaller, and I abstracted away the complexities of the disk transitions between the memory and the. Okay, of course, these are on the disk. Maybe I am loading them from the disk to the memory, that kind of stuff. So base and limit register by itself cannot handle this kind of complexities. We need more abstract mechanisms. Okay, so this is the second disadvantage of the base and limit registers. Any questions?
Hocam başka bir program çalışınca bunun base ve limit register'ları daha mı farklı oluyor yoksa aynı olabilir mi yani? Mesela iki tane
Are you asking about this or are you asking about this?
Bunu soruyorum evet hocam.
This one.
Mesela bir tane daha çalıştı üzerinde bir tane daha proses çalıştı.
True, if you are loading a third process, then it has its own base and limit registers.
Aynı olamaz değil mi bu? Sıfırla mesela 16.
No, if you make them the same, then this would happen. This would happen. I mean, if they are trying to use the same address, then the instructions will collide, and that's not good. If you are saying that write this out and load another process here, are you saying that? Bunun yerine başkasını mı koyalım diyorsun?
Hayır, yerine başkasını koymayın demiyorum. İkisi aynı anda çalışabilir mi? Onu soruyorum.
If they are at the different parts of the memory, yes they can. Ben sorunu anlamadım seni ya.
Ya benim sorum şuydu hocam, buna izin veriyorum ya, 0 ile 16384'te aynı iki tane proses çalışabilir mi? Yani base'ini ve limitini iki tane proses böyle yapabilir.
Nasıl olacak ki? Bu adam burada bir sıralama işlemi yapmaya çalışıyor. Sen aynı yere sort işlemi, arama işlemi yapan başka bir proses koymaya çalışıyorsun. Yani bir memory, bir byte tutuyor, başka bir şey tutamıyor ki. Yani onu sildiği zaman başka
bir şey için dedim, hani belli bir yere kadar daha kullanabiliriz dediniz ya, mesela 6 tane bölüme ayırdınız. 2 tanesini kullanabilir dediniz, bir tane proses.
Ha, sen bununla alakalı soruyorsun.
Bununla alakalı, onun için öyle dedim. Mesela 4 tanesi boş kalıyor. Yine adam öyle ayırmış mesela.
Tabii. Yani şimdi başka bir tane daha şey olsun burada. Let's say I have another process like that, and this one is larger from the memory too, and I have 1, 2, 3, 4, 5. I can put one here. Okay. So the blue one is here, blue 2 is here, and red one is here. So even though both of these programs are much larger than my main memory, I can run 2 of them at the same time. But not using the base and limit register. This is called virtualization, virtual memory and paging. We'll talk about them next week. Okay, but for this kind of thing to work, we need much higher level of abstraction. Okay, another question? Let's continue base and limit registers. Okay, another concept with the operating system abstraction mechanism is swapping. Okay, swapping is not an alternative solution for base and limit registers. Okay, this is some other concept. Swapping. Physical memory is not large enough to hold all the processes. Okay, maybe let's say this is my physical memory, and this is my process, and this is another process. Process A and process B. If I wanted to load both process A and B to the memory, both of them at the same time, I don't have enough space. So what do? I can run only a single process at the same time. No, there is a solution. There is a solution. I mean, note that A or B can fit to the memory. And I can load A or I can load B, but not at the same time. So they developed this technique called swapping. They say that okay, in swapping, write the entire program out to disk when it's blocked. Okay, when it is blocked. So swapping solves this problem of if my main memory is not large enough to hold more than one process at the same time, then don't load them. Don't load them at the same time. Just swap. If one process blocks, write the whole process to the disk and load the second one and let it run. This way, I can do the multi-programming. More than one program running at the same time in one. Another solution to this problem is virtual memory, and we are going to look at it later. Virtual memory. We will look at this virtual memory concept later. For now, we are looking at the swapping. Swapping is simply if a single process is blocked, then write that process to the disk so that I can have available memory for some other process. Okay. So when this process is ready to run again, because it was waiting for some kind of an I/O operation, then I can read it back from the disk and write it to the memory and let it run. And this is called swapping. It is called swapping. Okay, I can write to the disk and load it again and do the same thing with other processes. This way, I can handle processes if my physical memory is not large enough to hold more than one program at the same time. I can use this technique. Some people say that I can use this to compact the memory. What do I mean by compact memory? Okay, we will come to this one later. Maybe I should look at this one first. Let's say in my operating system, I have this program A. It has its own address space. Then I loaded process B, and it has its own address space. Then C. ABC and ABC are running at the same time. Then A is done. No, not saying that. Okay, ABC are running at the same time. And I want to run another program named D. Okay, named D. And I don't have enough space to load D because I have space only this much. D is going to be this much space. So what do? I write one of the block processes, for example this one of the block processes, to the disk. So this space is now available to load my program. And I load my program there, D. Okay. Since A is blocked, it is sitting on the disk. When the time comes for A to run again, because it is now ready, I can load A to this location, but B is there. I cannot load it. There is no enough space, so I can write B to the disk, and now I have enough space load A there, okay? Load A there. So this is the concept of swapping. If I don't have enough space, then write the block process to the disk and get some new space and use that new space to load new programs. Okay? So writing to the disk and loading them back is called swapping. It says that can use this operation to compact the memory. Sometimes I have pictures like this. This picture is not a good picture. Why? This one. Or this one. This one. It's called, these are called fragmented memory. Fragmented, parçalanmış memory. I have some space available here, and I have some space available there. Okay, maybe I have enough space to load A, but since they are fragmented, I cannot load A. I need a contiguous space to load A. So fragmentation is something bad for the memory. Maybe I can compact my memory using these swapping algorithms. What I do is that, okay, write B to the write all of them to the disk, D, B, and C. Then load them back. Okay. When you load them back, D will be here, B will be on top of it, and C will be on top of it, and I will have enough space to load another process. This process is called compacting. Okay. Okay. I can compact the memory that way, but it's an expensive operation. It requires many processes to be written to the disk and loaded again, so that I can have enough space. Okay. So this